On the 23rd of June, 2025, a rocket lifted off carrying something that had never left the surface of the Earth before. Not a satellite dish, not a GPU, not a sensor array, but a working quantum computer, shrunk down to fit inside a payload the size of a shoebox, and built to survive the most hostile environment humans have ever tried to compute in. Within days, it was orbiting the planet at roughly 330 miles up, silently proving something engineers had debated for a decade, that the strange, fragile physics of quantum mechanics could actually survive a rocket launch. This is not a story about a distant future. It's a story about right now, about a quiet, accelerating race between 3 different superpowers, a dozen billion-dollar startups, and the outer edge of physics itself, all converging on the same conclusion. Some problems can no longer be solved on the ground. They have to be solved in orbit. To understand why anyone would go to the trouble and expense of putting a quantum computer into space, you first have to understand what's actually breaking down here on Earth. For 70 years, computing has followed a simple, brutal formula. More performance requires more power, and more power requires more cooling. Every data center you've ever heard of, from the ones running your streaming service to the ones training the largest AI models on the planet, is fundamentally a heat management problem wearing a computer's clothing. Racks of processors generate enormous quantities of waste heat, and that heat has to go somewhere, which is why massive data centers are built next to rivers, lakes, and cooling towers, consuming staggering amounts of fresh water just to keep their chips from melting. At the same time, those same data centers are drawing so much electricity that entire regional power grids are starting to strain under the load, with some tech companies now openly discussing building or restarting nuclear power plants just to keep pace with AI demand. It's a problem that isn't getting smaller, it's compounding year over year as models get larger and workloads get heavier. And it's this exact bottleneck, power, water, land, permitting, heat, that has quietly pushed some of the most ambitious engineers in the world to ask an almost absurd-sounding question. What if we just built the data center somewhere the sun never stops shining and the cold never runs out? That place, of course, is space. And the pitch is deceptively elegant once you hear it laid out. In low Earth orbit, a satellite can be positioned to receive near-continuous sunlight without a single cloudy day, without a night cycle interrupting the flow of solar energy, and without a utility company sending a bill. There's no need for batteries or backup generators because the sun is, for practical purposes, always on. And when it comes to cooling, space offers something no data center on Earth can ever replicate: the vacuum itself. Heat can be radiated directly outward as infrared energy into the emptiness of space, which acts as an essentially infinite heat sink, without a drop of water wasted and without a single cooling tower built. One of the engineers behind this new wave of orbital computing described it plainly. The vacuum of space functions like a kind of cosmic air conditioning, with waste heat simply beamed away into the dark, and the only real environmental cost paid up front at the moment of launch. It sounds almost too clean to be true, and for years it was dismissed as science fiction. Then, in November of 2025, a small American startup proved it wasn't. That company is StarCloud, based just outside Seattle, and its story alone would make for a compelling documentary. Founded barely 2 years before its first launch, StarCloud sent up a satellite weighing about 130 pounds, carrying a single NVIDIA H100 GPU, a chip you'd recognize as one of the most sought-after pieces of silicon on the planet, the same class of processor powering the largest AI training runs happening today. Wrapped in radiation shielding and cooled by a system borrowed directly from the heat rejection technology that keeps the International Space Station livable, that satellite became the first entity in human history to train a large language model in orbit and to run a version of Google's open-source Gemini-derived model from space. It wasn't a stunt for the sake of a headline, although it certainly generated one. It was a working proof that a commercial, off-the-shelf, data center-class chip, 100 times more powerful than anything ever previously flown, could survive launch, survive radiation exposure, and perform genuinely useful computation while circling the planet. The market noticed immediately. By April of 2026, StarCloud had raised $170 million in a single funding round led by Benchmark and EQT, catapulting the company to a valuation of $1.1 billion just 17 months after its first public pitch. Reportedly the fastest a startup has ever reached unicorn status coming out of Y Combinator's accelerator program. The company's next satellite, StarCloud 2, is expected to launch before the end of 2026, carrying NVIDIA's next-generation Blackwell B200 chip, generating roughly 100 times the power of its predecessor, with cloud infrastructure partners including AWS, Google Cloud, and Crusoe, all flying hardware or software on the same mission to test what orbital compute can actually deliver. And the company's own long-term ambition isn't modest at all. Their published roadmap describes a 5-gigawatt orbital data center, with solar and cooling panels stretching roughly 4 kilometers on each side, a structure that, if built, would generate more power than the largest power plant currently operating in the United States, using a fraction of the land and water a terrestrial facility of the same size would require. But here's where the story shifts from impressive to genuinely strange, because raw AI horsepower is only half of what's actually happening above our heads right now. The other half, and arguably the more consequential half, belongs to an entirely different branch of physics, one that doesn't just process information faster, but processes it in a way that classical computers, no matter how many GPUs you stack together, can never truly replicate. That branch is quantum computing, and it turns out that space isn't just a convenient location for it. In some very real ways, it may be closer to a natural home. Quantum computers are famously delicate machines. Down here on Earth, the leading superconducting quantum processors from companies like Google and IBM have to be cooled to temperatures colder than deep space itself, just a fraction of a degree above absolute zero. Inside massive cryogenic refrigerators that look more like something out of a submarine than a server room. That's an enormous engineering burden, and it's one of the central reasons quantum computers remain confined to a handful of specialized labs rather than sitting in ordinary data centers. But there's a different flavor of quantum computer, one built not from superconducting circuits but from individual particles of light called photons, and for that particular architecture, space starts to look less like a hostile environment and more like an ideal one. Photonic quantum computers don't need the same brutal refrigeration. They need something closer to darkness, stillness, and a clean optical path, all three of which orbit provides in abundance. There's no atmospheric turbulence to scatter delicate photon signals, no ground-based vibration disturbing SENI. Side of optics, and once you're above the atmosphere, sunlight itself becomes an asset rather than an obstacle, since solar power can run the system without a single power line. This is precisely the reasoning behind that satellite launched in June of 2025 by a team at the University of Vienna, led by physicist Philip Walther. Their machine wasn't a superconducting chip. It was a photonic quantum processor engineered to use photons as its basic unit of information, exploiting the wave-like behavior of light, interference, and diffraction to carry out specific types of calculations, including a mathematical operation called the Fourier transform, which shows up constantly in signal processing and image analysis. Building it wasn't easy. The team had to compress an entire quantum optics laboratory down into a satellite payload small enough to launch, capable of surviving punishing temperature swings, radiation bombardment, and the violent vibration of a rocket launch. Engineering problems so severe that the assembly of the final flight-ready hardware, completed in a clean room at the German Aerospace Center's facility in Traun, took a team of 12 people, 4 weeks of preparation, followed by an astonishingly fast 11 working days to actually build. Once in orbit, the payload became fully operational, and the team behind it has been candid about what this mission actually proves and doesn't prove. It is not yet outperforming classical computers on a meaningful task. What it does prove, for the first time in history, is that a genuine quantum computer can survive spaceflight and continue functioning once it gets there. An unglamorous but absolutely foundational milestone. The same way the first working transistor in a lab wasn't useful for much on its own, but made everything that came afterward possible. And the applications researchers are actually excited about aren't abstract. One of the clearest near-term use cases is something called edge computing, the ability to process data directly on a satellite, right where it's collected, instead of beaming raw data all the way down to a ground station, waiting for a classical computer on Earth to crunch the numbers, and then transmitting the results all the way back up into orbit. Think about a satellite scanning a forest for the earliest signs of wildfire, or scanning ocean surfaces for the faint thermal signature of a distressed vessel. Every second spent shuttling that raw data down to Earth and back is a second lost. And every transmission burns power that a small satellite doesn't have to spare. A quantum processor capable of running certain calculations directly on board, without ever touching the ground, could compress that entire loop down to something close to instantaneous, cutting both the energy cost and the response time, in situations where minutes, sometimes seconds, genuinely matter. Rather than waiting years for a dedicated satellite integration process, the plan is to test the hardware live during an actual flight, subjecting it to the real radiation, thermal extremes, and mechanical stress of orbital travel, in order to answer the exact question that's been hanging over this entire field. Can sensitive quantum hardware survive not just being in space, but getting there in the first place? The stated long-term goal is even more ambitious than a single test flight. The two companies have described plans for something called a Space Quantum Computing Center, envisioned as a cloud-linked next-generation data infrastructure hub using quantum algorithms to optimize entire satellite fleet operations, accelerate the analysis of deep space data, and eventually offer quantum computing resources as a cloud service to commercial and government clients. The reasoning behind the urgency is straightforward. As satellite constellations multiply, as direct-to-device communication networks expand, And as real-time intelligence gathering from orbit becomes more complex, the demand for onboard computational power is climbing faster than classical hardware, constrained by weight, power, and heat limits, can realistically keep up with. Now, here's where the story takes its sharpest turn, and where the phrase, classical computing can't follow, stops being a marketing slogan and becomes something closer to a law of physics. Because while American and Korean teams are still in the proof of concept phase with quantum computation itself, China has already built, Hutchison is actively scaling an entirely different category of quantum infrastructure in orbit. One built not around raw computing power, but around a kind of security that classical technology, no matter how advanced it ever becomes, is mathematically incapable of matching. It's called quantum key distribution, and understanding why it matters requires understanding one very specific, very strange rule of quantum physics. You cannot copy a quantum state without disturbing it. Physicists call this the no-cloning theorem. And it isn't a design choice or an engineering limitation. It's baked into the fabric of quantum mechanics itself. What that means in practical terms is almost science fictional. If you encode a secret cryptographic key into individual photons and send them from a satellite down to a ground station, any attempt by an eavesdropper to intercept and read that signal along the way will unavoidably alter it, leaving behind a detectable fingerprint. Classical encryption, no matter how mathematically sophisticated, offers no equivalent guarantee. A sufficiently powerful adversary, and increasingly a sufficiently powerful quantum computer, can in principle break classical encryption without ever being detected in the process. Quantum key distribution flips that entire equation. The eavesdropping isn't just prevented, it's physically impossible to hide. China has been building toward this vision for nearly a decade, and the pace of progress has only accelerated. It started in 2016 with a satellite named Michus, a roughly 600-kilogram spacecraft that cost around $100 million to build and launch, and which achieved the world's first successful transmission of a quantum-secured key between space and the ground. It was a landmark, but it was also enormous, expensive, and difficult to scale, requiring ground stations weighing over 13,000 kilograms just to receive the signal. Then, in July of 2022, China launched something radically smaller, a microsatellite called Jinan-1, weighing barely 23 kilograms, about 1/6 the mass of its predecessor, paired with portable ground stations weighing under 100 kilograms rather than over 13 tons. That miniaturization wasn't just a neat engineering trick. It represented something close to a 45-fold reduction in cost, alongside a 2 to 3 order of magnitude increase in the rate at which secure keys could actually be generated. In a landmark study published in Nature in March of 2020, the research team behind Jinan-1, led by physicist Pan Jianwei, demonstrated real-time quantum key distribution between the satellite and multiple ground stations scattered across China, and then, remarkably, all the way to a ground station in Stellenbosch, South Africa, establishing secure quantum-encrypted communication across nearly 12,900 kilometers, spanning the northern and southern hemispheres. During each individual pass, the tiny satellite was capable of generating more than 1 million bits of secure cryptographic key, transmitting roughly 250 million individual photons every single second. China has already signaled its intention to launch additional quantum communication satellites in 2026, including one positioned in geostationary orbit, with an explicitly stated ambition of building a global constellation by the end of the decade, the physical backbone of what scientists have started calling the quantum internet. It's worth pausing here to appreciate just how deliberate this strategy is, because it isn't simply about faster or shinier technology. It's about infrastructure ownership, in the same way that the country which lays the fiber optic backbone of a region often ends up shaping the technical standards everyone else has to build around. China's rapid, low-cost miniaturization of quantum satellite hardware positions it to become the default supplier of secure quantum communication infrastructure for any nation that hasn't built its own. And other major powers clearly understand the stakes, because they're now racing to build parallel systems of their own. The European Space Agency is preparing to launch its own answer, a satellite called Eagle-1, using an all-optical approach with phase-encoded pulses to establish Europe's first end-to-end satellite-based quantum key distribution system. It's designed as the seed of a much larger European quantum communication constellation, tightly integrated with the European Union's broader secure connectivity infrastructure and its long-term quantum communication strategy. Meanwhile, in a parallel but related effort focused not on future-proof physics, but on hardening what already exists today, IBM and the aerospace company Voyager Technologies announced in April of 2026 that they had established the world's first post-quantum cryptography-secured communication link between the International Space Station and the ground. What's notable about that achievement is that it didn't require new, exotic quantum hardware at all. It was a software layer, deployed on a small onboard computer already aboard the station, wrapping existing legacy applications in encryption specifically designed by the National Institute of Standards and Technology to resist attacks from future quantum computers, all without needing to rewrite a single line of the underlying application code. Together, these two approaches, physically unbreakable quantum key distribution and mathematically hardened post-quantum cryptography, represent two different bets on how to secure the coming era of orbital infrastructure. And right now, multiple governments and companies are hedging by pursuing both simultaneously. China isn't stopping at secure communication either. It's pursuing an equally aggressive parallel track in raw orbital computing power, treating space not just as a place to send secrets safely, but as a place to actually crunch numbers at scale. A space computer called Aurora 1000, built by the company Como Space, has already logged more than 1,000 days of continuous operation aboard a Jilin-1 satellite, and a more powerful successor, Aurora 5000, equipped with a dedicated graphics processor, is scheduled for trials sometime in 2026. Even more ambitious is a project sometimes referred to as the three-body constellation, a network of 12 satellites carrying an 8 billion parameter artificial intelligence model, which, by February of 2026, had completed 9 months of in-orbit testing, successfully demonstrating key capabilities in space-based networking, distributed computing, and live model deployment. That project is described as the early seed of a far larger initiative China calls star computing, which envisions an eventual network of 400 satellites dedicated to AI training and 2,400 satellites dedicated to inference, together capable, according to projections, of tens of thousands of petabytes of inference capacity and millions of petabytes of training capacity by 2030. And by 2035, enough distributed computing power, according to the plan, to support hundreds of millions of autonomous AI agents operating simultaneously. Whether every piece of that roadmap survives, contact with the brutal realities of orbital engineering remains to be seen, but the scale of ambition alone tells you how seriously the idea of moving computing infrastructure off the planet is now being taken at a national strategic level. So where does all of this actually leave us? And what does classical computing can't follow really mean once you strip away the hype? It's tempting, in a story like this, to reach for the easy, dramatic claim that quantum computers in orbit are already outperforming everything we have on the ground. That's not quite honest, and it's worth being precise about it, because the actual state of the science in the middle of 2026 is more interesting than the exaggerated version. Where the classical can't follow claim becomes rigorously, provably true isn't in raw computation yet. It's in security. The physical guarantee behind quantum key distribution, that any eavesdropping attempt necessarily leaves a detectable trace, is not something classical cryptography can ever replicate, no matter how many more transistors you cram onto a chip or how many more years of Moore's law you wait for. That's not a performance gap that better engineering will eventually close. It's a structural difference rooted in the actual rules of physics, and it's the reason multiple governments are willing to spend hundreds of millions of dollars putting increasingly small, increasingly capable satellites into orbit specifically to carry that guarantee down to Earth. And that distinction actually makes the bigger picture more compelling, not less, because it means we're watching two genuinely different revolutions unfold in parallel, on the same rockets, sometimes on the very same satellite buses. One revolution is about raw horsepower, solving the earthbound crisis of power and cooling that's currently strangling the AI industry, by moving classical GPUs into orbit where the sun never sets and the cold is free. StarCloud's trajectory from a 2-year-old startup to a billion-dollar company with NVIDIA's most advanced chips already lined up for its next launch shows just how fast investors believe that particular bet is going to pay off. The other revolution is about something classical engineering can never brute force its way into matching, a form of security and eventually a form of computation that depends on genuinely exploiting the strange behavior of quantum particles rather than simply making classical hardware smaller and faster. China's decade-long build-out from the enormous, expensive Mishas satellite to the tiny, cheap, wildly more capable Jinan-1 shows how quickly that second revolution is maturing from laboratory curiosity into deployable, scalable infrastructure. Both of these stories are happening at the same time, often described in the same headlines, and often conflated by people trying to make the story sound more dramatic than the facts currently support. But you don't actually need to exaggerate any of this to find it extraordinary. A satellite the size of a small refrigerator, quietly orbiting 500 kilometers above your head right now, is capable of generating a cryptographic key that no computer on Earth, quantum or classical present or future, could ever secretly intercept without giving itself away. That's not science fiction. That's operational technology, tested across 3 continents, published in one of the most rigorously reviewed scientific journals in the world. What comes next is where this story gets genuinely uncertain, and honestly, that uncertainty is part of what makes it worth watching closely over the next few years, rather than dismissing it as another overhyped tech headline. Engineers still don't fully understand how quantum hardware ages under years of continuous radiation exposure in orbit, since every mission flown so far has only been running for months, not years. Nobody has yet demonstrated a photonic quantum computer in space performing a calculation that a classical computer genuinely could not replicate in reasonable time. The milestone that would transform this from a feasibility story into a performance story. The cost curve is also still deeply uncertain. Launch prices have fallen dramatically over the past decade, but building, radiation hardening, and maintaining specialized quantum payloads at scale is an entirely different cost problem than launching a standard communication satellite. And there's a geopolitical dimension that can't be ignored either, because whoever builds the first truly global entangled quantum communication network effectively sets the technical standard the rest of the world either adopts or is locked out of. The same way early internet infrastructure decisions shaped decades of digital policy long after the original engineers had moved on. China's head start in miniaturized, low-cost quantum satellites gives it a real strategic advantage in that race right now. And Europe, the United States, and South Korea are all moving specifically to avoid being permanently dependent on someone else's orbital backbone. What's clear, watching all of this unfold in real time across 2025 and 2026, is that the question is no longer whether computing infrastructure moves off the surface of the planet. That question has already been answered quietly by a 130-pound satellite training a language model above the Earth, by a photonic quantum processor surviving its first winter in orbit, and by a network of Chinese microsatellites handing off unbreakable cryptographic keys between continents thousands of kilometers apart. The real question now is how fast the rest of the pieces fall into place. How soon a quantum computer in orbit performs a calculation no classical machine on Earth can match. How soon a genuinely global, entangled quantum internet goes from a research roadmap to operational reality, and which of the countries and companies racing toward that finish line right now gets there first. For decades, space was where we sent our satellites to look outward, back down at Earth, or out toward the stars. For the first time in human history, we're now sending computers into orbit specifically because some of the hardest problems in physics can no longer be solved from the ground at all. That shift, quiet as it's been so far, may end up being one of the most consequential technological turning points of this decade. And it's happening right now, a few hundred kilometers above your head.